So one early AMD story, I remember in the early days of YouTube, people would post, these things they would do, and it was just everything very low res and just ad hoc back then. There were none of the YouTubers, that wasn't a thing yet. But I remember these two guys, they had two different computers, one AMD and one Intel, set up on a table with sideways and the side off and everything. So you could see the chip, there's a chip that's running right now. And they had it running some process, they're playing some game or something like that, something that used most of the CPU's power. And they said, we're going to, while it's running at full power, we're going to pull the heatsink off and see what happens. And of course, they were monitoring the CPU speed and health at the time. They took the heatsink off the Intel one, and it very gracefully slowed itself down based on its own temperature, so that nothing bad happened. They pulled the heatsink off the AMD chip, and it just kept going full bore. And it would get hotter and hotter and hotter, and then you heard this pop, and it was off. And they walked over to the machine, and it had exploded with enough power to make a hole in the bottom of the table that the computer was sitting on. So that's the early days of AMD. But I would say now they seem to be in a stronger position than Intel. We'll see. I have a lot of hope for the future. I see all kinds of ways in which the next step of computing will be exponentially better than what we have now. But sorry, you guys are going to have to understand some physics, because quantum computing is going to be a big deal, especially for machine learning. I believe that the way we will use quantum computers in the future will be similar to the way you use GPUs now, where you write a program, it's running on a CPU, it prepares a computation. That computation goes to the GPU and runs, then comes back to the CPU, then you interpret the results and use them somehow. That's how we use GPUs. Something like that will occur for QPUs, quantum processing units. As of, I guess, 2015, that was when the first quantum computers were available to the public. IBM had theirs, it was only like 5 qubits, but very noisy, but anybody in the world could use it. Now on Amazon, there's 4 GPUs: IonQ, D-Wave, Rigetti, and one other, I forget. And of course, IBM keeps having newer ones to come out. There's a lot of retraining your brains would have to go through to understand what's actually going on. Google's working on it too. Like you said, the logical qubit just means a theoretical qubit without errors. And behind it could be 1,000 or 2,000 actual qubits to make that one non-error qubit function. I don't know, but it's going to take a while. In the 60s and 70s, actual silicon computers were this noisy. So think about it as we're in the 1970s, quantum computing. And eventually we will get to the 2000s. And they will be useful, I believe. All right, let's jump in. And I want to say something about your upcoming homework. Each of you your homework for Thursday will be a notebook file, just like usual. And in the last cell is where the TA is going to run his thing. So you should have some object, a model object, that's already loaded in that notebook, which means if you did everything from the beginning in Google Colab, you're fine. If you loaded it from somewhere else, you need to run it in Google Colab so that the model object, whatever you call it, is loaded with the object. And it needs to have a predict function. And he's only going to pass it one thing, the data in his own little test set. And the format of it should be very simple, similar to what you get when you import data sets .mnist, there is a you can look up the standard PyTorch, what's it called, PyTorch Vision or PyVision, I forget, maybe it's PyTorch Vision. That's the way this is formatted by standard. That's how his will be formatted. And I'm going to let you guys coordinate with him on Discord. He knows all this. He's created the data set. He can coordinate with you. If things don't work the first time, that's okay. You guys can iterate back and forth. I definitely want you to have something done by Thursday, but if it doesn't work because of some little idiosyncrasy, that's okay. You can iterate back and forth with him. Questions?
Are we supposed to check with him and get his test yet?
No, because he's going to be the one to run it. He's going to go into your notebook and load his data set into your model without you having access to his data set ahead of time.
So if we normally on our last neural net, we just like process the data, like normalize it. You want us to make another method so it normalizes the data?
Inside Predict, we better do whatever.
This is the image data.
Yes, exactly.
Do you want there to be like a model class?
There needs to be some kind of class that has a predictive variable. And you can call model, you can call whatever you want. You should have a little sentence of documentation saying, this is how you use it. And run it on, either the training set, a test set, or a piece of the test set. Have a cell there where it was used and it produced predictions. So this thing has to return just a list of the predictions. All right, any other questions? All right, let's get back into language and the complications and complexities thereof. I once met a guy. I was interviewing at some, NLP company, and I was talking to them all, and one of them was a really smart PhD guy. And I said, what did you do your thesis on? He said, comedy. Oh, interesting. So he used, NLP techniques, whatever, to study comedy. So my first question was, awesome, what was your favorite joke? He said, oh, I don't have a sense of humor. I just study it. He didn't enjoy jokes. He didn't have a favorite joke. He didn't have a favorite comedian, nothing. But he studied comedy. And I think comedy is one of those things that obviously the computers don't understand. But I think it's hilarious when people talk about comedy in an unfunny way, such as this. Humorous discourse offers an open-ended invitation to appreciate and enjoy an ambiguity among contrasting perspectives with incompatible affective valences. What? This is like Spock talking about comedy. I had an English teacher in college, or in high school, who said that the essence of comedy is incongruent juxtaposition. And she was trying to chide us all for doing senior pranks. Anyway, comedy is hard for a computer to grasp. Another thing that's hard to grasp is little things about the way we talk, like paper burns up, but a house burns down. You get, you go in a house, you get maybe in a ship, but on a boat, on a plane, other things you get in. How do you choose these? What if people disagree? And these don't translate across languages well. So language is a spoken phenomenon, and there is a interesting topology to the situation. Now, a couple of you were in De Palma's class that I was a guest lecturer at recently, and there's going to be some repeats here. So sorry about that. But topology is the study of spaces or surfaces and how they map onto each other. Usually high dimensional spaces, how they map onto each other, or things that are connected and what they map onto. And the rules of topology are that you don't break places where they're connected, and you don't make new connections, and you don't make holes, basically. So this is a topological break. This is against the rules of topology. To take something that's connected in a certain way and break it apart, the seams. Now, when you talk, you are necessarily saying one word at a time. And I know I've mentioned some of this before, but think about the topology of that situation. You are taking, a word, and each of those are connected one to another. And any word can only be connected to two other words at a time, right? However, when you think about the meaning of a sentence, you can understand that there's sometimes words that are connected to three other words. Like Jack gave Jill a book. Logically in your head, you know that gave has a giver, it has a recipient, and it has a gift. Three concepts are directly connected to give or gave. In your head, you know this. You're able to take this thing, which topologically is a chain, and somehow interpret it as this. And English uses word order to let you do this. Like, how would you know that it wasn't Jill that was the giver? Jill's the recipient because of word order. Now, there are languages which don't rely on word order. They rely on suffixes, things like that. And the purpose of those suffixes is to help you find this from this. It's a topological break that your brain is doing. Okay. WordNet is a fun data set to play with. People have collected a whole lot of words that are connected to other words. It's like a giant source network. We've talked about senses. Each sense is a different definition of a word. And if you look in WordNet, each sense gets, the letters that map to like fool, but also the definition specified. So that, fool number 2, dull number 1, Mark number 9, Patsy number 1, ball guy number 1. The meaning would be, a person who's gullible and easy to take advantage of. Mug number 2, soft touch number 1. So right now, I'm just going through more linguistic stuff that you should be exposed to so you know about it if you need to do NLP. A WordNet graph might look like this. This is one of the things that WordNet has. Let's say you have wagon is a wheeled vehicle. Self-propelled vehicle is a wheeled vehicle. Wheeled vehicle has a brake. Wheeled vehicle has a wheel. So we have all of those meanings and their relationship to other meanings, whether they're a has a or an is a or has part, or is an attribute of or an antonym of or similar to. So using stuff like this, you can kind of see how reasoning systems could be built, right? automated reasoning, if you could do it accurately at scale, is one of the holy grails of artificial intelligence. Okay, here's another test. Now, I apologize that we're switching gears again and again very rapidly, but I just want to get through a lot of material. I'm exposing you to this. You can watch the video again later and you can go down on a deep dive on each one of these. This is something called SEMEVAL, semantic evaluation. This is a contest they gave out for a number of years. They might still do it sometimes. What they do is they provide a whole bunch of sentences, and humans were tasked with grading them on similarity from 1 to 5. 1 being not similar, 5 meaning they mean the same thing. Using different words, but they mean the same thing. Such as, I have a big boat, or I'm the proprietor of a yacht. Those should get a 5. Humans will mark that with a 5. Whether a computer could also get a 5 for that is another question. And it gets very difficult when there's a lot of implied knowledge. Okay, a person is on a baseball team, a person is playing basketball on a team. Obviously, they don't mean exactly the same thing, but they will probably get a 4 because they're both about people being part of a team playing a sport that involves balls. Our current vehicles will be in museums when everyone has their own aircraft. Car needs support. This is less similar than that last pair. What would you guys give that pair? What would you give it?
A 2 solely on the fact that the car, like, you were decommissioning the whole train time that you are being for decommissioning vehicle.
Uh-huh.
But if it said, like, our place are gonna be museums, that's, it's like, you're still referencing the car even.
Yeah. Okay, any other thoughts? Okay, I don't think anyone can give it a 5. Any of you give it a 4? Raise your hand. 3, raise your hand. 2, raise your hand. Any ones? All right. Last one. A woman supervising is instructing the male workers. A woman is working as a nurse. No 5s, I don't think. 4, 3, 2, 1. All right. So the way they do this SEMEVAL task is they literally have 3 people vote on every one of them, and then they take the average. And you're trying to write a program that will guess the average of what the general population would do. It's a very hard task. Okay. Let's look at this one. There's another one called SEMCore. Okay. So, given a set of words and definitions, like we talked about before, you have some word like stand, and maybe there's stand 1, stand 5, stand 10, maybe others. When you see words in the wild, can you tell which definition it refers to? An electric guitar and bass player stand off to one side. You as a human know instantly that this is not talking about the fish. It's well the same as bass, but it's definitely not talking about it. You know that instantly. Probably when we got to the word guitar, your brain was primed to understand it was that. Now, there are other definitions of bass that have to do with music. Could be a bass guitar. It could be just the bass range and sound. It could be a stand-up bass, which is not a guitar, but string instrument. Your brain is doing something here. Can we duplicate that in software? A guy named Lesk came up with one way to do that. And the idea was to look at words in the definition and words used around the instance. Look for similarities. Like in this sentence, it is a heavy metal that is denser than most common materials. Lead is soft and malleable and also has a relatively low melt. So if you look at two definitions for LEAD, one of them pronounced lead, the other one pronounced lead, the computer doesn't know which one it is. Well, this one, the definition is to direct on a course or in a direction. None of those words appear around or in a window around this example. A soft, heavy, metallic element with an atomic number 82. Some of those words do appear. This is how Lesk was able to do sense disambiguation. And that's what the task is about. Figure out which sense is actually being used. The Schutz algorithm is more elegant because it has to do with word vectors. Now, remember we talked about vectors being just location in high dimensional space that represents a word. So I want you to think about it as representing a meaning instead of a word. So let's say that we had every one of those senses that was in the dictionary provided to us. And the word mark, M-A-R-K, had 10 different senses. It had a different vector for each of those. And the word L-E-A-D had 5 maybe. And every one of those has its own vector. So then the task is, when you see it in the wild in a new sentence, you see L-E-A-D. Which of the existing senses is it? You just assume that you know everything. You're just trying to figure out which of the things you already know this new word is. So you got your right. The bottom one, your leadership is about direction, impact, strategy. So what you would do is you would take this word and create a vector based on the words around it. You do the same for some other example. And the hope is, not always works, but the hope is that the vector you create from this will maybe appear here and you use the closest one from the dictionary. And hopefully that will get you the medal, and this one will get you lead. Definition about leading. That makes sense? All right. Another way is to use neural networks, and when you're processing some sentence using maybe a recurrent neural network, at every step you will get a new vector, and that's what you use to do a similar thing. You maybe have, several definitions of find, and as you're processing it using something like the LSTM we talked about, you get a vector after processing the word found, and you try to see which one it's closest to. And if it's closest to the ninth definition of FIND, then you use that one. And again, this is not a totally solved science, so there could be other ways that one of you will discover someday. Okay, Riemannian math is wonderful math. You should be aware of it. It's the math of mapping from one space to another. It has a lot of implications in machine learning. Everything up to an activation function is a homeomorphism from one space to another. And when you're embedding your data, whether it's words or events or things about people or movies, if you embed them in a high dimensional space, that space doesn't have to be Euclidean. It can be something else, and it can be warped, and it can be weird, it can be hyperbolic, it can be spherical, it can be all kinds of things. Let me ask you a question. Imagine you were two-dimensional. You were maybe a square, and you don't understand up and down. It's just beyond your comprehension. all you know, forward, backward, left or right. What if you get really angry at your parents? You're like, screw them, I'm out of here. You run away from home and you just go in a perfectly straight line as far as you can get. And after a long, long time of traveling, straight ahead of you, you see your home, the back side of your house. You're like, what's going on? How would you guys explain that?
Would it be on like a sphere?
Yeah. How do you know you're on a sphere without having to go all the way around?
Without being able to like curvature? Just.
Well, yeah, without, you don't know curvature. You don't know it could exist.
Well, if you go forwards, like your plane, or you can still like physically see what's behind you, like this, like on like a flat plane. So if they like, it's supposed to just.
Well, think about on the earth. If you're talking to a flat earther, how could you work together in a relatively small area without the sun, determine that you're on a sphere? Let's say within, a couple 100 miles. No sunshine needed, no stars,
I mean, like if you decide to have a light source or something,
no light source.
you could have them stand, and then you could go 100 miles in a direction, and then if you could like see them at the same level on a flat plane, if they were at a higher point, yes.
There's a lot of variance though in altitude on Earth. Well, one way that Riemann proposed is you can make a triangle. If you're on something spherical, then the degrees of the angles are going to add up to less than 180. Now there are hyperbolic spaces where it adds up to more than 180. Riemann also, he gave us generalized math that applies to all kinds of spaces that are curved in all kinds of ways. And there's a whole, deep math behind that, and tackling that, understanding that would be one of the ways to go to improve machine learning. Okay, so this is a hyperbolic space. This is called the Poincare disk. Imagine mapping all of a flat plane that goes on to forever, mapping it to a circle. One of the ways they talk about doing this is, if you think of a flat plane that maybe goes on forever. And then above it, you put a hemisphere mirror. You can think of, this point right under it maybe refers to right here, then this refers to here, and this refers to here, and this refers to here. And this point right here on the edge refers to infinity in that direction. And this point refers to infinity in that direction. You get the idea? And you can map an infinite plane onto a circle. And that's what this is, which means this point is infinitely away from the edge, everywhere on the edge. This represents a straight line. This represents a straight line. Every one of these lines is a straight line. Remember how these lines might be curved if they were represented in a mirror sphere above the plane. When you may put it into the Poincare disk, those are straight lines. You'll see in a minute why we look at this. So if you have all of the plane mapped onto the Poincare disk, if you have a point here and a point here, any two random points, and you want to find the real distance between them, this is your equation. So even though it's actually a unit disk, the radius is 1, and everything in there is within 2 of each other in real space, the space it's representing, distances are calculated this way. The reason why we do this is because, and this is beautiful when I first heard it, the Poincare disk is the continuous version of a discrete hierarchy. Discrete means there's points that are separate from each other. Continuous means it's smooth, like real numbers. We think in terms of discrete concepts. All the meanings in our world are discrete. If you were to map them onto a Poincare disk, one good way to think about it is in the center, you would have maybe the word thing. And here you could have, maybe living thing. And here this could be animal, and this could be mammal, and this could be, ungulate, and this could be giraffe, and so on. As far as you want to go, because remember, the edge of the circle is infinitely far away, so you always have room to add more specific things. Specific things toward the edge, general things toward the middle. If we organize our word vectors like this, then it makes it easier for some machine learning models to learn from data, learn about the world, to make conjectures. If you want to do a deeper dive on this, the real work was done at Stanford starting in 2017. And it's really interesting stuff. Okay. We're about to jump into transformers. So any questions or thoughts before I switch gears yet again? All right. Transformers are the #1 model being used right now in NLP, NLU, and they're starting to make their way into visual models. They are GPT-3, GPT-4 when it comes out, BERT, Lambda, this big model like Google that someone thought was conscious. You guys hear about that? Remember that? These are all transformers. They work better than anything else we've ever had. People are continually surprised at how well they work. They're not the final answer. They have big weaknesses, but they're the best we have for now. So let's look at them. And we're going to start off with thinking about the transformer as a black box. Then we're going to peer into the black box a little more, and a little more, and a little more. And each step is going to add on the rest. So pay attention to each step. From the outside, we can give it, je suis étudiant, and it gives us back, I am a student. That means this transformer was trained to accept French sentences and give us English sentences. Now, here into the black box 1 level, we get encoders on the left and decoders on the right. The encoder takes this, je suis étudiant. It does a whole lot of math. Then the decoder, we're able to pull out of that decoder, I am a student. The encoder is actually a whole bunch of steps. Right here, it only shows 6. In real big ones, it's a lot more. I don't think anyone really knows. They haven't publicized the code behind GPT-3. We don't know, but it's a lot. And basically, these word vectors get ingested into this encoder. It does a whole lot of math, passes it to another encoder that digests it all again, digests it all again, whole bunch of times. Then it passes it to the decoder. Decoder does some digestion, passes it to the next decoder, which also actually starts at the bottom here. This second decoder, it gets the digested output from the first decoder and direct access to the final encoder. Same thing with the next one, and the next one, and the next one, and the next one. Then finally it's ready, and it gives us, I am a student. Now, let's look inside of one of those encoder blocks, just one of them. We've got two things. We got the self-attention network and a feed-forward neural network, just means a simple neural network to process the output of the attention mechanism. Now, this self-attention block right there, that is the key insight of the transformer. The stuff that's going to go on inside there, which we're about to get into, is the key insight. That's what started the transformer revolution. I can't remember exactly when it was, maybe 5-6 years ago, maybe 2017 or something, but the paper was called Attention is All You Need, as a play on the Beatles song. It was focused on what's about to look at inside here. Guy was basically saying, you don't have to know about language, you don't have to know about linguistic structure, you don't have to know about factors, temporal or sequences or anything, just use attention for everything. Like turtles all the way down. It's attention all the way down. Okay, now we're going to get into the guts of the self-attention network. Now, if you remember, we had that sentence a while back, I shot an elephant in my pajamas. And the hardest part for a recurrent network to learn was that I, at the beginning of the sentence, needed to be somehow connected to the pajamas at the end of the sentence. It had to read through each token, updating its internal state, carrying along the right information. And when it got to elephant, for the purposes of what's wearing pajamas, ignore the elephant. And remember that I token from way long ago. And that long-term relationship can only learn those if it sees millions of examples. So one of the solutions was, hey, let's let every word pay attention to every word directly, instead of just, through several tokens. So transformers let every word connect to every word. Of course, that can introduce tons of noise. So we have to do it with big vectors. We have to do it a lot of times. The way we pay attention to every word is this self-attention mechanism. Every word means self-attention. The sentence is paying attention to itself. Let's imagine we're going to take 3 word vectors and we're going to input them into the transformer, into the encoder. Each word is embedded to a vector. When this thing started out, we were using 512 vectors. I don't know what's being used right now. And each vector, obviously they're not linked 4. Just imagine there's 512 there. Okay. The vectors are going to go into the self-attention mechanism. So we start off with these X's represent the incoming vectors. We get these from a library. We get these from, things like the glove vectors we talked about, or they could even be the character-based LCMs you generate. Doesn't matter, but you have vectors to start with, and you put them into the self-attention mechanism. It is a whole lot of digestion in here, and it outputs Z vectors. And the Z vectors are passed on to the next step. So how do we get from X to Z? That's what goes on in the self-tension mechanism. And eventually end up with R vectors after that. Okay. Here. Instead of having 3 words just using Julian, let's just consider 2 words. Thinking machines. That was actually a big company years ago. They were making the best computers in the world for a while, and now they're gone. Sadly. So we have an X vector, and we want to get to that Z vector. Start with X, we're going to digest it with the self-attention mechanism, and we're going to end up with a Z vector. Now, the self-attention mechanism, it assumes 3 matrices. Q, K, V. The query matrix, the key matrix, and the value matrix. Now, just posit that these matrices exist. We randomize them at first, and then the system optimizes them over time. That's what the training does. But we're just going to assume they exist. We will generate these query vectors, key vectors, and value vectors with those matrices. Just like all the other things that have worked in machine learning, somebody really smart tried something out and it just worked. This is one of those things. So just come along for the journey and we'll look at how it works. We start off with that X vector. And we take the X vector, we multiply that Q matrix by the X vector, and we get a Q vector. For thinking, we get a K for thinking, and we get a V for thinking. We also get the same thing for machines. So we already had those matrices. They were coming from the trained model. We multiply them by our word vector, and we get these 3 new matrices, 3 new vectors, right? Q, K, and the V for each word. Now, at the end here, just for the word thinking, I'm going to have this little multiplication. Q times K. I'm using the dot product. So when you take the dot product of 2 vectors, you get a scalar, just a number. The query times the key thinking gives us, let's say, 112. The query 1 times key 2 gives us 96. So this is interesting. Here, what we're doing, this is all just for the word thinking. We're using the same query vector for thinking, multiplying by both of the key vectors. In fact, for a long sentence, you multiply by every key vector. Then you do it again for the second word. So for the second word, we'll have Q2, and we're going to multiply Q2 times K1, Q2 times K2, Q2 times K3, and so on. Then we just have this rule where we divide by 8. There's some interesting math behind that. Don't worry about it too much. But in the end, the softmax is used to make sure that all of these values add up to 1. So you can think about them as probabilities. This is attention. The attention that one word gives to another word is the value between 0 and 1. Every word in this sentence will be giving some of its attention to every other word. And in this case, we see that thinking is going to give 0.88 of its own attention to itself and 0.12 of its attention to the next word. Machines will do something else. If we did its equations, it would just do something else. Okay, now we're going to take our V value and we're going to multiply it by that. So this V vector, what you see here is this should be 0.88 as bright as that one, and this one is 0.12 as bright as that. This just trying to describe the idea that's going on behind the scenes. We're going to take 0.88 of this vector and 0.12 of this vector, add them together, and that gives us C. I'll repeat that. So we use those three large matrices that already existed, and of course they get adjusted in string. The Q matrix, the V matrix, and the K matrix. We use those to make Q vector, K vector, and V vector for every word. Then we multiply the Q's by the K's, so that from the perspective of that first word, it's going to be giving 0.88 attention to itself, 0.12 attention to the next word, et cetera, et cetera. Then we do that same process for every word. Then every word knows how much attention it's going to be paying to every other word. Then we apply that attention to the V vectors, the value vectors. So from thinking's perspective, its Z vector is mostly its own V vector and a little bit of the vector for number 2. From V2, from the machine's perspective, the second word, it could be totally different. If you had a third word or a fourth word, they would all be different.
Are you only looking at the next word, or are you looking at all the other words?
All the words.
I mean, are you looking back to?
Yes. So machines will look back at things. And big models run on big memory, sometimes can have, a couple of pages of text instead of one sentence. You can see how this can be sent to train. The best models out there, they probably spend $100 billion just to GPU time. Quotient similarity is later on in a sense, but also this dot product is like a kind of like a cosine multiplication. So in the end, after it all gets processed out, maybe you have this Z vector, and maybe this first Z vector is closest by cosine similarity to some other word. But we're getting ahead of ourselves because we really have to do this multiple times. Anyway, this is the deepest guts of the self-attention mechanism. This is what self-attention is. And it happens all inside of that self-attention block, which is inside of an encoder. Every encoder block has those two things, and self-attention is doing what we just described, all of this. And it does it in a way that's matrixized, so it's in matrices, and it can compute efficiently on a GPU. The matrix version looks like this. You just do a soft max of Q, KT, that square root of dx, just 8, and then multiplied by V, and you get this Z matrix, which is all of those Z vectors. You get it all at once. And you do this, a whole bunch of times. This is, with a slightly more detail. Instead of just a feed forward above the self-attention, you do some adding and normalizing, 2 different feed forwards, then some more adding and normalizing. And it just gets worse and worse and worse. Anyway, the main strategy these days is to take this, make it bigger, bigger, and bigger. And every time they go bigger, like let's say they double the size of everything, right? double the amount of data they train it on, they do get an increase. They get maybe, maybe it's a 0.1% accuracy, or maybe something more interesting and hard to describe. They get a lower incidence of stupid errors and more things that sound interesting. Some of these conversations with GPT-3 have been really interesting, where people pose it with a question, the answer is back in a way that sounds logical. They even had GPT-3 write a New York Times editorial about AI and why we should be scared. And he would say things like, don't worry, we're not going to take over. Now, if you dig into the truth a little bit, they really prompted it in a certain way. They prompted the engine to generate text in a certain way, and they would prompt it a bunch of times, like for every question, maybe 5 times, and then choose the best answer. They would piece together these pieces into an editorial. So yes, no human actually generated any sentence, but a human curated and cherry picked. So as far as I can tell, what I truly believe right now, these models are the best we have, but they do not understand what they're talking about. They're best described as highly sophisticated word salad. But they're pretty awesome as word salad goes. It's kind of amazing that anyone thought to try all that math, right? It just seems kind of like a long shot. The fact that it works is pretty crazy. Can you imagine how many models that didn't work or tried before this? Decades of models, really. Any questions? Are any of you, oh yeah.
Do you know if this model's like akin to anything else, or if this like technique is first of its kind?
Self-attention built on previous attention models that we have been using attention for a long time.
It's the same math.
Not the 3 matrices, more like using maybe 1 or 2 matrices to determine the attention, or you just have a static set of attention. You learn that this node will always pay this much attention to that. But this is built on a lot of other research. One of the ways they made this actually work was they started off with just 1 encoder and 1 decoder. It didn't work. They're like, let's make 2 of them, then 4, then 8, and 16. And it still didn't work. Then they said, inside of here, which we didn't go into, you can have multiple heads, they call them, where each head is learning that those attention matrices, or 3 attention matrices, separately. So instead of 3, maybe you get 6, or maybe you get 10 times that. And then they're like, well, that kind of worked. So let's double everything. And they did it again. Oh, let's double everything again. And they just kept adding on to it, piling on, piling on, piling on. And we're still seeing small improvements. So people are going to still keep doing it. I don't find it interesting at all. It's not how humans learn. All right. Thank you, everybody.